Hello, and welcome back to Physics 41, University Physics 3. So we are now on the second lesson for the chapter on alternating currents. So far, we have described alternating current and alternating voltages in terms of phasors, where we can write the instantaneous current and voltage as a function of the current and voltage uh, amplitudes and the angular frequency and time. So for this lesson, we will be talking about resistance, reactance, and impedance. So these three physical quantities actually have the same unit, the unit of resistance, which is ohms. So let's first start by putting a resistor in an alternating current circuit. So a circuit where the voltage source or the power source is alternating between positive and negative values, for instance. So if you have a resistor in an AC circuit, the voltage phasor and the current phasor actually alternate in the same phase. So the voltage and the current phasor actually rotates in the same rate, in the same angular frequency omega. And they are, aside from they're rotating the same angular frequency, they are also in phase. So if the voltage phasor is here, the current phasor is also here. If the voltage phasor is here, the current phasor is also here. So if you try to plot it in terms of a sinusoidal graph, this means that the current and the voltage go to a maximum and go to a minimum, and in fact go to zero at the same time. So that's what happens if you connect a pure resistor, only a resistor, to an AC circuit. So I will just summarize the voltage amplitude or the peak voltage relationship between with the resistance. So the peak voltage, this is the peak voltage or the voltage amplitude, is just equal to the current amplitude times R. So it's just similar to the DC circuits version, Ohm's law, V is equal to I times R. So you can actually replace the peak voltages and the peak voltage and the peak current, or the current amplitude and the current voltage, by the RMS version, and you will still get V is equal to I times R, because the square root of 2 factor will just cancel each other out. So in this case, this is our instantaneous voltage. It's the voltage amplitude cosine omega t, and the current amplitude is instantaneous current is current amplitude cosine omega t. So in that case, we say that the voltage and the current are in phase. They go to maximum and minimum at the same time. They go to zero at the same time. Now, what if you have an inductor in an AC circuit? So this is a symbol for inductor. L is the inductance. So in this case, the voltage will actually lead the current by a quarter cycle, or by 90 degrees. So if this is the current phasor, then the voltage is actually ahead by 90 degrees. So the relationship between the voltage amplitude is actually I times XL, where XL is what we call the inductive reactance, and it's proportional to L and the angular frequency omega, the frequency of rotation. So in this case, both the voltage and the current still move at or still rotate at the angular frequency omega, but just so happen that the voltage leads by an angle of 90 degrees. So for the instantaneous voltage, it looks similar with the previous expression, but there's a plus 90 degrees here. This is what we call the phase angle. So the angle between the voltage phasor and the current phasor. So the phase angle is actually important when you are discussing about phasors. So for instance, in the previous slide wherein we discussed about resistors in an AC circuit, the phase angle of a pure resistor in an AC circuit is actually 0. So it's just V cosine omega t. So again, if you take the RMS version, you can write this as VI times XL. So take note that XL here, something like has a role of resistance. So reactance is basically just, you can think of it as the resistance of the inductor. So an inductor has what we call self-induced EMF. This is a measure of how much the inductor resists the changes in or variation in current. So basically, it's still a resistance. Its unit is actually similar to that of the resistance, which is ohm. Now, in the case of a capacitor in an AC circuit, so this is a capacitor, C is what we call the capacitance. So the voltage actually lags. It's behind the current phasor by 90 degrees. So in this case, the relationship is similar to that of in an inductor, I times X, but this is now XC, where XC is 1 over omega times C. So the reactances, the X are what we call the reactances, they all depends on the capacitance and inductance in the case of the inductor. So this is what we call the capacitive reactance. So the voltage now lags by 90 degrees. So the phase angle is negative 90 degrees. So for a resistor, the phase angle is 0. For a pure inductor, the phase angle is positive 90 degrees. But for a pure capacitor, the phase angle is negative 90 degrees. But if you have all of these elements in a circuit, then the phase angle is no longer 90 or negative 90 or 0. So in this case, the reactance is actually inversely proportional to the capacitance. So again, you can think of the capacitive reactance as a resistance of the capacitor to changes in current. Now, let's summarize the result of the resistance versus the reactances of our circuit elements. So these are our circuit elements. These are the amplitude relationships. These are the quantity. So inductive reactance XL is omega times L. Capacitive reactance XC is 1 over omega C. So you will notice that the resistance doesn't depend on omega, on the angular frequency. So meaning at all values of the angular frequency, if you graph the resistance versus omega, you'll just get a flat line. It's constant, it's the same. But for the inductive reactance XL is directly proportional. So if omega increases, XL will also increase. So this is the graph of XL versus omega. And in the case of the capacitive reactance, it's inversely proportional. So at large values of omega, the capacitive reactance actually decreases. So, by the way, what is this omega? So the omega is the angular frequency. If you will recall, the angular frequency, omega, is actually related to the frequency, which is 2 pi times the frequency. So in most cases, we will only be dealing with the frequency. So actually, for example, in our alternating voltage line in the Philippines, it's 220 volts VRMS, and it's alternating at a frequency of 60 hertz. So that 60 hertz is given by this F. So if you multiply that with 2 pi, you get the angular frequency. The angular frequency, that is what we see here. So there will be times that you will be using F instead of omega, because usually it's the frequency F that is given, not the angular frequency. So for inductors, you will notice that the reactance is large for large values of omega. So for high frequency. So for high frequency of alternating sources, alternating voltage, or high frequency of variation, then inductors react or resist high frequency current. So they block high frequency current. So they only let low frequency current to pass through the inductors. That's what this means. In the case for capacitors, it's inversely proportional. So meaning they react, or the reactance is large for very low frequency oscillations of the current and voltage. So capacitors resist low frequency current and low frequency voltages. So that's why any device with this property is what is also called a high pass filter, because they act like a filter. They only allow high frequency oscillations or high frequency current and voltage to pass through the device, such as a capacitor. So a capacitor can act as a high pass filter. So if you now have a resistor, capacitor, inductor series circuit connected to an AC source, then you can now describe the total or the net resistance reactance of the system as Z, where Z is what we call the impedance. So you can think of it as the net resistance, net reactance of your circuit. So it's square root of R squared plus XL minus XC squared. So in this case, or what this tells us, similar to DC currents, where the voltage is I times R, and which means that current is inversely proportional to resistance, meaning current will always follow the path of least resistance. So similar to here, the current is inversely proportional to impedance, meaning the alternating current, on the other hand, or in the same case, will also follow the path of least impedance. So in an LRC series circuit, you can calculate for the phase angle, the angle between the voltage phasor and the current phasor as this. So they are all related to the reactances and the resistance of your circuit elements. So I will not go into detail about the LRC AC circuit. So I will just point out one very interesting application. So actually, one application of an LRC series circuit is the radio. The radio in your phone, or in your the radio used by your grandparents or maybe parents. But we will discuss that in the next chapter. So one important application of LRC series circuits, which involves impedance, is the measurement of body fat by bioelectric impedance analysis. So you can see here you have an overweight person, and electrodes are attached to this person, which actually supplies an alternating voltage, but it's very small. It's not fatal. A very small AC voltage with a frequency of 50,000 hertz or 50 kilohertz. So it's a very high frequency AC source. So the attached instruments actually gives or measures the current. Actually, it's RMS, current RMS, and the VRMS, voltage RMS, the current and voltage. So by using that data, you can now have an idea of the impedance of the body. And that impedance actually depends on the amount of water and fat along the path followed by the alternating current. So by measuring the impedance, you can actually measure the body fat of a human body. So that's one interesting application of impedance. Okay, so let's now have some examples on resistance versus reactance. Okay, so we have an inductor in an AC circuit. So the current amplitude, so the maximum current in an inductor in a radio receiver is 250 microamperes. So this is I, the maximum current. When the voltage amplitude, so this is the maximum voltage, is 3.60 volts at a certain frequency of 1.60 megahertz. So this is in the AM, amplitude modulation, AM frequency. Okay. So we have two questions. What inductive reactance and inductance, inductive reactance is XL, inductance is L, are needed to achieve these values? And if the voltage amplitude is kept constant, what will be the current amplitude through this inductor at 16 megahertz and at 160 kilohertz? Okay. For the first question, you are asked to find the inductive reactance. You are given the voltage amplitude and the current amplitude. So for letter A, we will use the voltage amplitude relationship for inductors in an AC circuit. So we can actually solve for the inductive reactance as V over I. In this case, BL, because this is the voltage across the inductor. So you divide 3.60 volts by 250 microamperes. Micro means times 10 to the negative 6. So you take that into account, and you will get 1.44 times 10 to the 4 ohms, or 14.4 kilo, 14,400 ohms, or 14.4 kilo ohms. So that's for letter A. That is the inductive reactance. So knowing the inductive reactance, I can now solve for the inductance, L. So since XL, the inductive reactance is just omega times L. And take note, this is just frequency. This is not angular frequency. So this 1.60 megahertz, that's actually just F. So we need to use the formula 2 pi F for the angular frequency. So solving for L, so L is just equal to XL over 2 pi times the frequency. So XL is this one, 14,400 ohms. 2 pi times the frequency is 1.60 megahertz. Mega is times 10 to the power of 6. So you substitute all that values and you will get 1.43 times 10 to the negative 3, or 10 to the negative 3 is milli. So 1.43 milli. The standard unit for inductance is Henry. So milli Henry. 1.43 milli Henry. So this is for letter B. So for the third problem, no, this is still for letter A, sorry. This is the inductive reactance and the inductance. So for letter B, for the second problem, if the voltage amplitude is kept constant at 3.60 volts, what will be the current amplitude to this inductor at these two values? Okay. So for letter B, we solve for I. So I is just V. So we just manipulate this equation. I is just VL over XL. But our XL now will now vary because the frequency is now different. So we have two frequencies, 16 megahertz and the other one is 160 kilohertz. So we need to use this version or this formula for XL, 2 pi F times L. So you have VL over 2 pi F times L. The first frequency is 16 megahertz, so 16 times 10 to the 6 hertz. The second frequency is 160 kilohertz, or 160 times 10 to the 3. Kilo means times 10 to the 3 hertz. So, using those two values, let's go here. So, you will actually have two values of current. For the frequency of 16 megahertz, the current is actually 25 times 10 to the 6 amperes, or 25 microamperes. And for the frequency of 160 kilohertz, so you just substitute the value of F. The current amplitude is actually 2.5 times 10 to the negative 3, or 2.5 milliamperes. So the frequency and the current amplitude are actually inversely proportional to each other. So as you can see in this equation, so the larger the frequency, the smaller the current amplitude. So you will now see that in a radio, you can actually have two modulations in a radio. You can actually change the current amplitude, or you can actually change the frequency. If you are changing the current amplitude, that's AM, amplitude modulation. You control the current, you modulate the current. But if you are controlling or modulating the frequency, that is FM, frequency modulation. So that's basically radio, AM, FM, amplitude modulation, frequency modulation. So here's a summary of our results for this problem. So let's now go to the second problem. So we have here a resistor and a capacitor in an AC circuit. So this is our AC circuit. We have a capacitor with a capacitance of 5 microfarad. Micro again is times 10 to the negative 6. And a resistor with resistance of 200 ohms. Now, we are also given the instantaneous voltage of our resistor. So this term here, this is actually the peak voltage, VR, or the voltage amplitude. And the term 2500 radians per second is actually our angular frequency, omega. So it's V cosine omega t. That's actually the instantaneous voltage. So if you will recall, the instantaneous voltage for a resistor in an AC circuit is the voltage amplitude cosine omega t. So that's the form of this given value here. So we are asked to derive an expression for the instantaneous circuit current I. So this is a series circuit. So the current that flows to the capacitor is just the same current that flows to the resistor. So it's a series circuit. We're also asked to determine the capacitive reactance of the capacitor, so XC. And we are asked to derive an expression for the instantaneous voltage, VC, across the capacitor. So take note, the voltage, all of the voltages in our circuit elements are also alternating or fluctuating. Okay, for the first problem, so we are asked to find an expression for the alternating current, the instantaneous current I. So the instantaneous current is actually just so we can actually measure first. It's easier to measure or observe the resistor. So for the resistor, the current there that flows there is just equal to the voltage there, the instantaneous voltage there, over its resistance R. So we already know VR, it's this one. So you will have 1.20 volts cosine 2500 radians per second T divided by the resistance, which is given as 200 ohms. So we can now write an expression for I. So 1.20 volts divided by 200 amperes, that will give you 6 times 10 to the negative 3, or 6 milliamperes, cosine 2500 radians per second T. So this is now our expression for the instantaneous current. Take note, the instantaneous current is time dependent. So this term here, this is our current amplitude I, the maximum current. So the maximum current in this case is 6 milliamperes. Okay. So determine the capacitive reactance of the capacitor. So XC is just equal to 1 over the angular frequency times the capacitance. So we are given both. Omega is 2500 radians per second. The capacitance is 5 times 10 to the negative 6 farad. So you just drop the unit radians. So when you're going outside of the angular frequency space, you drop the radians unit. But if you go into the angular frequency space, you need to add a radians unit. So in this case, we will drop the radians unit. So anyway, if you are calculating resistance or reactance, the final unit should be in ohms, provided all of your units are in standard unit, SI unit. So you will actually get 80 ohms for letter B, the capacitive reactance. So for letter C, you're asked to derive an expression for this, the instantaneous voltage across the capacitor. So if you will recall, the instantaneous voltage for a capacitor is actually given, actually look like this. So for letter C, VC is equal to the voltage amplitude across the capacitor, VC, cosine omega t minus 90 degrees, because the phase angle for a capacitor is 90 degrees. So we'll use this. So we first need to solve for the voltage amplitude across the capacitor. So in order to do this, we use the voltage amplitude relationship. So it's just I times XC. So I is the peak maximum current or current amplitude. XC is this one, 80 ohms. So 6 milliampere times 80 ohms, that will actually give you 0.48 volts. So knowing this, we can now write an expression. So take note, this is an expression because this is time dependent. It depends on time. So we now have VC is 0.48 volts cosine 2500 radians per second T, and since we are writing our angle in terms of radians, so we need to convert 90 degrees into radians. So that is minus pi over 2 radians. So this is now the expression for the instantaneous voltage across this capacitor. So take note, the voltage changes with time. And the maximum voltage there is 0.48 volts. Okay. So that's it for this lesson. So in the next lesson, we will be talking about how to calculate power in alternating circuits. I will see you again in the next lesson.